My name's Ray Toes. I'm from New Zealand. Yeah. That's all right. And I've made a study of cycles. And when I start talking, I'm going to be talking about stuff that doesn't seem like it has anything to do with fundamental structure of the universe, but it's going to gradually meander into that. So, in 1977, I was performing analysis of economic cycles in New Zealand, trying to do some forecasts for businesses. And I wasn't looking for cycles, but cycles were there. They jumped out at me and they said, "You've got to study us." And so I started looking to see what were the what periods were present in this data. I had 22 economic variables in New Zealand. And at that stage, I didn't know that you were supposed to do it in terms of frequency. I did period across here. Now I know you're supposed to do frequency. But as I varied the period, there were 4 clear peaks in the strength of the cycles amongst these 22 variables. And I gave periods as 4.45 years, 5.9, 7.15, and 9 years. And so I then began to study those and use them, and they worked. And a bit later on, I decided, well, some of these cycles were too slow. You could make money in some of the markets like this, but if you really want to make money, you want some faster cycles. So I got some weekly, I'm confused now whether it was corn or wheat, one of those things that had weekly data. This was basically using annual data. And I got weekly data and I studied it, and I found there were a whole set of cycles present in those things that were all related. Now these 4 cycles were related. I put 4 little arrows here, and those arrows correspond to exactly if taking 35.6 years and divide it by 4, by 5, by 6, by 8, and you got those points which match very accurately to the cycles periods that were found.
Right. Can everybody see well enough, or turn off the light? Yeah, maybe we'll turn off.
Yeah. So, and then at that stage I realised that this other set of cycles I'd found in the corn prices were the same frequencies as 2 octaves of the white notes on the piano with 2 of the black notes thrown in, E flat and B flat as well. Not every one note was there, but nearly every one. And then I realised 4, 5, 6, 8, that's a major chord in music. That's a just intonation scale, it's an exact fit. And I thought, something's going on here. And this was the 1970s. And if you remember then, there's the Mandelbrot set had come out and a couple of other things, all to do with nonlinear systems when they were the rage. And I thought, nonlinear systems, they might do this. And so I started to look at nonlinear systems in relation to it. And as I did that, I came to an idea that if you had one cycle, for example, if you had an 11-year cycle that was affecting something in the climate, if we imagine that it's non-linear, let's suppose we're growing wheat, and this variable is going to go from, I showed you in the picture, so this variable is going to go from too little of something to the right amount to too much. And as that happens, the wheat's production is going to go up and it's going to reach a peak and then it's going to go down again. So over one 11-year cycle, which we go from here to here and back, this one goes up, down, so we get 2 cycles. So an 11-year cycle in temperature or rainfall or whatever it was that was doing it could cause a 5.5-year cycle in wheat prices or wheat production, which would affect the prices. And in actual fact, the best periods I had at that stage for the sunspot cycle, which is 11 years, is 11.08 years, and the best period I could get from the wheat ones was 5.54 years, exactly half. So this seemed to be a reasonable explanation that non-linear relationships were causing these things to happen. So I then started to say, well, let's say that, this one's probably a bit hard to see. This has got the planets here and the moon here, and the planets are affecting the sun. The various configurations affect things that happen in the sun. And I've just got a whole lot of different things happening in the sun here, sunspots, solar output, solar flares and that, and they're all coming over here and affecting lots of things on the Earth in terms of its magnetic field, its temperatures and its pressures and all sorts of stuff. And this is all coming down to affect crops and other animal things and stuff, and affecting the economy and all through. So this was just supposed to be a picture that showed there are many things affecting each other. And if we've got nonlinear relationships in all of them, then what's going to happen is we're going to get this production of harmonics from things, But once a second thing's established, if it's got a non-linear relation to the next thing in the chain, it's going to produce harmonics of itself again. So I came to this idea that there would be harmonics of harmonics. I now think that this picture, although it's still sort of right, it's, there's actually probably a simpler story. So what I did is I said, let's assume we've got one frequency and it makes harmonics of itself. So we've got frequency 1 and it produces frequency 2, 3, 4, 5, 6, all on there. And then as a result of it producing frequency 2, that frequency now starts producing multiples of itself, harmonics of itself. So it produces 4, 6, 8, 10, 12, 14, etc. And 3 produces 6, 9, 12, 4 produces those. And you can see what's happening. 12 pops up a lot. 11 and 13 only turn up once each. So 12, the 12th harmonic is going to get a lot more energy because it's getting it via a number of different ways. But that's not the full story. The full story is a little more than that because the 4th and the 6th and the 8th harmonics I put in there were already produced in multiple ways. So here I've just put one way of being produced for the 4th harmonic from there and one from there. So it gets 2 ways. So when it comes to taking the multiples of the 4th harmonic, it's got twice as much energy to start with, so they get 2 each. And the 6th has got 3 times as much, so they get 3 each. So the numbers that come out the bottom here get fed back in on the side, and we get this sort of structure. So this is saying that there are actually 8 ways of getting from the 1st harmonic to the 12th. You can go from straight 1 to 12, you can go to 2 and then times 6, or you can go to times 2 times 2 times 3, you can go 4 times 3 and so on. It all adds up to 8 ways. So then I started looking at this and I started adding it up. How did that go? But there was a second factor that comes into it, and that is, as you produce harmonics, when you have like a violin or a guitar or something, it will make harmonics, but generally the higher order ones are weaker. So I'm assuming that there's some sort of a function where as we go to higher orders it gets weaker. It might be, I've just given an example here of 1 over h or 1 over h squared, or you might call them 1 over f and 1 over f squared, drop-offs and the thing. I'm going to assume that that's happening as well. And then this is the actual number of ways each harmonic can be produced by this simple calculation that I showed you there. And you can see that multiples of 12 especially like to appear, and that the numbers are going up. The ways of producing certain harmonics is going up. But then I'm going to superimpose on this decline, and that as the higher order harmonics are getting weaker. And when I do that, I've just simply taken here how many ways it gets produced and divided it by the harmonic number. And you'll see that there's certain ones are predicted to be stronger. Now, when we look at this, we notice 48, 60, 72, 96. If I divide those by 12, it's 4, 5, 6, 8. So here's my little friend, the 4, 5, 6, 8 proportions I found in the New Zealand economy, turning up. And there, but also these other ones, the next strongest ones, turned out to be the rest of the notes in the musical scale, including 2 flats. So the thing comes out there is the just intonation music scale comes out from this very simple calculation of putting in harmonics and harmonics of harmonics and adding up how many ways you can make each one. So this pattern, so this calculation I call this is the harmonics theory. First of all I started thinking it was just little things happening on the earth and little bits, and then I found when I went to the Foundation for the Study of Cycles, I found that Edward Dewey had observed the same cycles with the same periods in different countries in different time periods and different data, and the same ones kept popping up all over. So it was quite a wide variety. And in fact, when I started to look at things like some things outside the Earth, when I started to look at the rotation, the orbital periods of the planets and the satellites, and looking for communalities amongst those, the same periods kept popping up. So it's something that goes beyond the Earth. And Edward Dewey of the Foundation for the Study of Cycles also came to that. Now this one's a little bit hard to see, you'll see it better in the printed version, but this one here I've run, started on a log scale, I've gone up to 10 to the 18th harmonic. I've skipped a bit, I did it in steps, like I did up to 10 to the 6th on the computer, then up to 10 to the 20 and 10 to the 30, and as computers got faster, this one runs up to almost 10 to the 54. And we see that there's a huge number of sort of background ones that are there all the time. But I don't know if you can see it, but there's an envelope here that's bobbing up and down of the strongest harmonics. And I managed to work out why that happens, but there's a pattern going on in them. And what I've done here is I've taken the envelope there of the very strongest harmonics and I've made a graph of it, and this is going through to 10 to the 40th. And we see that there are some particularly strong peaks which I've labelled 1, 2, 3, 4, 5, 6, 7, 8 there, which are at more or less equal ratios of scale. So they are, the first one happens at 34,560, or at 17280, and that are both pretty much the same peak. And they are all more or less at equal ratios. So every 10 to the 4.5 power, roughly, all the way through, there's another very strong harmonic. And so, if we look at the structure of the universe, the picture's just slightly too big. Can you make it a teensy bit smaller? So that's it. There's a little bit missing on the sides, I think.
Because losing that. Move the
The
projector
edges.
closer.
Move the projector.
Or
No,
bring the
they're further
screen
away.
forward. I think bring the screen forward might be
Closer,
better.
closer.
Because people will be able to see it
Yeah,
better
come a
with
bit
that.
closer, yeah.
Come really careful, it might fall.
I'll pull this side, you pull it side.
Because this thing, I made it fall before.
That's it, that's good, thank you, yeah. So, if we take from the Hubble scale, I've put in black darker here the things that have got sort of unique names: galaxies, stars, planets, moons. I've called these X and Y. There's no obvious things at those ones. There's cells, atoms, and nucleons. And if you put in here the value for the scale of the Hubble scale and divide repeatedly, you actually get, for this one you get 0.5 angstroms, which is the Bohr radius of the hydrogen atom, and at this one you get 1.3 femtometers, which is the radius of a nucleon. And these ones give reasonable measures of all of those things from those other peaks. And there are, in that thing, there are also secondary peaks, typically at ratios of 12 apart from the main ones, and we see these, such things as irregular galaxies or giant stars or terrestrial planets are at a smaller scale than the planets themselves. And the same thing is overhead like bacteria and viruses, you have the atom with the electron. So that whole structure there looks a lot like the structure that's predicted by this very simple calculation. Just to mention the scale of these, that one's about 1.7 kilometres and about 5 centimetres. Why there's nothing at those? There's several possibilities on that, but that's an interesting little mystery. Right in the human scale, right? Now, after I'd been doing this for about that much, I discovered there's a place called the Foundation for the Study of Cycles, and I visited there, and there was a man called Edward Dewey. Unfortunately, he died
Soon after.
He died in the late 70s, about the time I was working on this, but it wasn't until about 89 that I went to visit there. And he had this table. As I read through his stuff, first of all I thought I discovered all this, and then when I saw this I thought, he just discovered this pattern of the cycles, but he never worked out why, because he lived in a time when this study of nonlinear systems wasn't there, so that I had that advantage on him. But he had this period of 17.75 years, and he repeatedly doubled it, and halved it, and tripled it, and thirded it, and he produced all these periods, and he's underlined the ones here for which there are common cycles found. Now, there are a few other common cycles that he did find that occurred in many different things. I should mention he collected data on hundreds of different things, many hundreds, and he found thousands of cycles, and other people did too and contributed, and they had a huge catalogue of them all. But the interesting thing was, here he had a figure of 35.5 years, and what I'd found is my ones were all fractions of 35.6 years. I had a quarter, an eighth, and a sixth, and I also had a fifth, which doesn't fit in this table, but it does exist. He did have a cycle for that. And so this was a big confirmation that what I was finding was the same thing that he had found, and a couple of other people had found essentially this same sort of pattern. This is just a histogram of the number of reports running on a log scale from 1 to 100 years. There's a couple of more interesting ones just below 1, 0.33 and 0.4 and 0.66 of a year. But there's certain periods where there's a lot of cycles reported at 6 years, at 11, and so on. And here there's this little peak at around 35 to 36 years, a little cluster there. So that's just analysing how many reports there were in the various cycles.
Before you go back, can you go back to that slide?
Now what?
This slide here. Who did that histogram?
I did,
You did.
yeah.
Was that from the,
But it's from data from the Foundation for the Study of Cycles.
okay, did you use the card catalog there, or?
No, I used one that it was in electronic form.
Okay, when did you get that? See, I did one of that catalog too.
Yeah, yeah. Oh, okay, yeah, yeah.
Yeah, and
I've got several different versions of this. There's one that Dewey did, and there's one that I did, and there's another one that I didn't. Yeah.
okay, well, I'll
Okay.
discuss mine tomorrow.
Yeah. Okay. Now, Dewey came up with some. I'll call them Dewey's laws because they pretty much are. He said everything that's studied by man that can be made into a time series has cycles in it. Now, you can say the lottery numbers don't, and you'll probably find one or two things like that. but everything that's measurements of real things in the real world has cycles in it. And it doesn't, and even when you've worked out the cycles, there's always cycles in those as well. They're not uniform, they have some amplitude and frequency modulation and so on. There are common cycle periods that exist in many seemingly unrelated fields of study. For example, one of the really strongest ones is the Canadian lynx. They trap them for fur, and there's a 9.6 year cycle on that. The population of this animal multiplies by 10 and then divides by 10 every 9.6 years. They've got records from the Hudson Bay Company going back to the 1700s, and it's done this repeatedly throughout, although the numbers got down a bit more recently, that never quite got the recover as much. And they said this was due to the fact that it ate a particular thing, a rabbit, and that it was a predator-prey cycle. But that theory doesn't hold up because it also turns up in tent caterpillars, some are in the United States, and salmon in the Atlantic, and a couple of other things, and even human heart attacks occur on this cycle. So human population goes tiny little oscillations on that one as well. So this is the sort of pattern you get of things that seemingly unrelated. And one thing that could be a possible explanation on it was that the ozone levels do fluctuate on that cycle. These cycles with common periods exhibit cycle synchrony, meaning they reach their peaks and troughs together. Sometimes you'll find one that's an inverse of the other because you're measuring it upside down, as it were. Many of the commonly reported cycles exhibit simple ratios of 2 and 3 and their products between them. So that was Dewey's little chart with proportions of 2 and 3. Some of the observed cycles that fit these patterns are outside the Earth. So we have to really digest this. It means that all the stuff that's going on, all these fluctuations we're seeing in economies, in the weather, in the way at which things grow and all this sort of stuff, they are things that are arriving here. They're cosmic variables, right? So we have to have this understanding that something cosmic is going on. Dewey was very reluctant to come to that conclusion, but he finally did, because when he'd analysed these other things, he found that some of them were beyond the Earth. Another researcher at a similar period to Dewey, who was in America, was a guy by the name of Alexander Chizevsky, and he was a Russian, although he left Russia and went to live in France because it was about the time that Kondratiev, who studied cycles, said there was a 53, 54-year cycle in the economy, got sent to Siberia, and he didn't want that same fate, so he left. Incidentally, I was at the conference for his centenary in Russia, which was the first time they started to discuss cycles again after the communism fell. So that was quite interesting. And this is what he said. And this is a very poetic statement, but every part is incredibly meaningful as well. Life is a phenomenon. Its production is due to the influence of the dynamics of the cosmos on a passive subject. Passive subject. It lives due to dynamics. Each oscillation of organic pulsation is coordinated with the cosmic heart and the grandiose whole of nebulous stars, the sun and the planets. Now the passive subject's interesting because as humans we've got these inflated egos and we think we're the cause of everything that happens around us. I urge you to study cymatics, Hans Jenny cymatics, where he vibrated powders and fluids with just a couple of simple frequencies, and he's got cases where powder being vibrated by just 2 frequencies arranged itself to make it look like a centipede with lots of little legs, and they all go moving. And this sort of thing, that can happen from 2 frequencies. So when you've got thousands of frequencies coming, you can make a human being. Right? So this is the way that I would summarise where does this theory fit in. It doesn't contradict general relativity or quantum mechanics. I know there's a lot of people who have the odd niggle with those theories, and that's fine. it does have a huge argument with the Big Bang Theory. The three limits of the universe. Now what I've plotted here is radius or wavelength this way and mass or energy this way, they're being equivalent things. There's a limit to general relativity, which is the black hole limit, which is m divided by r, is a thing that comes to a constant. In quantum mechanics, we have a limit of m times r comes to a constant. So quantum mechanics domain is this little strip down here, and general relativity is this little strip here. You can probably measure some things from them elsewhere, but that's the areas where they're strong. Harmonics theory, which I'm describing to you, talks about the structure of the universe, and it works only on the radius or the wavelength of things, the spacings of things, and it works off here, but it does continue right across. But because it will sometimes meet these other ones, we get the situation where sometimes the mass will come in as important, like when we look at black holes, we'll see that their masses do follow harmonics theory because their masses are directly proportional to their radius. And in quantum mechanics, the reverse, we'll get the same sort of thing happening there. Edward Dewey said, insofar as cycles are meaningful, all science that has been developed in the absence of cycle knowledge is inadequate and partial. Thus, if cyclical forces are real, any theory of economics or sociology or history or medicine or climatology, and I might add or physics and or astronomy, that ignores non-chance rhythm is manifestly incomplete, as medicine was before the discovery of germs. Now that's a very, very accurate statement. It's I see in every branch of science that I look at, I find that I can find stuff out that other people didn't know. And I can tell them, and often they'll disagree. And then 5 years later, I'll see someone publish a paper saying, hey, this thing, it's actually like this. And they can find things that I'd worked out long ago because of this understanding of the cycle nature of things. So this is the axiom this is the preferred form of the axiom that I came to for the harmonics theory. The universe consists of a standing wave which develops harmonically related waves, and each of these does the same. Now in physics, the first bits are standard physics, standard music if you like, musical instruments and so on. But each of these does the same as the bit that harmonics theory says. You keep on feeding those in and making harmonics. In a one-dimensional system like a guitar or violin string, you don't get that each of these does the same. The harmonics that are made are just the harmonics and that's it. But in 2 or 3 dimensions, because you get interaction of the dimensions, if you have, say, the air in this room is in a vibration, it will get compressed in 3 dimensions. So you get a compounding effect of the pressure in the middle of the room if you have that. And that will make a new point, new seeds. The harmonics of that will make new seeds. It will be new centres that make new waves from them. So that's the key understanding was my insight into working this out, that I don't believe anyone had understood before. I've done simulations on the computer of 2 and 3 dimensional systems to show this really does happen. How long's the longest cycle? First of all, I thought it's going to be something to do with the Big Bang's 14 billion year sort of period. But what I did is I fed in quite a few measured cycles in the range 600 million years down to about a month or a little less. And all the ones that were common cycles that I knew about in that range, I fed them in. And then I took that graph I had produced that said what the pattern is predicted to be, and I compared the pattern that it was on a log scale. I'm just sliding it along and seeing how well it matches at each point, and trying to find, just moving a 10 increment each time. And I started at 10 billion years, because it's got to be at least that much, and I went along and it went wiggle, 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 and then it started to get a bit bigger, and then suddenly it did these huge spiky peaks here. Now, there's multiple of them, and the reason there's multiple is very simple. The structure, when you move it by a ratio of 2, is extremely similar, because we saw there was lots of cycles at ratio 2. So when you move it by a ratio of 2 higher or lower, it still fits the data very well, but not quite as well as when you hit the correct period, which I've given here as 1.4821824 times 10 to 23 years. Those digits might not all be accurate. I can say pretty certainly that it should be accurate to 4 digits, probably to 6, but it might be all of those. The reason that I've got all of those, I'll get to a little later, but that's showing that very clearly that the theory fits the observations in the range 600 million years down to about a month extremely well if we use that period. There's no other ones. You can see that randomly it just doesn't fit in other places anything like what it fits there. This is a little table showing in the range of years that we're used to in the commonly observed cycles. I've started at 586 million years here. What I've done, each little block here, I've got ratios 2 like Dewey had across, and I've got ratios 3 down. I decided to give away the diagonal thing. And then between these blocks, I've got, whenever there's some other ratio, there's a ratio 11 between this set and this set, then 5, then 13, then 5, then 7. Now, when I had the one earlier, I'll go back to that one because it's important to see that. This one here with all the peaks and troughs, I put at the top here the ratio between the very strongest cycles, and it goes 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, 2, 2, 2, 3, 2, 7, 2, 5, 3, 2, 2, 3. You can see it keeps going 2 a lot, 3 quite often, and every so often there's a 5, and occasionally there's some other prime, 7 there, 11 there, 13 there. And you'll see that these peaks occur between every ratio of 5, there's another peak. And where there's another ratio like 11 or 13, the troughs go much deeper because the energy is having to move from one set of cycles to another set that's very different, and it takes a long time for it to do that. So that pattern of the 11 and 13 that occurred in particular order there, here's the 11 and here's the 13. Now the 11 occurs between these ones in the 100 million year range and the sort of 10 million year range. And the 13 occurs between the ones in the 1,000 year range and the 100 year range, roughly speaking. And so when I first, before I knew about the accurate periods of these ones, I found this 13 there and I thought, that's not right. That should occur much further down. But when the 11 appeared there and they're the right distance apart, I then realised that I'd been assuming that 14 billion years was the period of time, and it's really not. It's really this much, much longer period. That then will fit and produce the 11 and the 13 exactly as they should. But the longest cycle is vastly longer, that 1.4 times 10 to the 23 years. 10 to the 13 times the age of the universe, according to the Big Bang, I say is a cycle that has occurred many times in order to produce this whole set of harmonics. And we can see in here many of the common cycles like 11-year sunspot and 22 and 44 during the sun, and all these ones that Dewey had. I've slightly altered his values from 17.75 to 17.79, and I've altered mine from 35.6 to 35.59. And I chose these values because a Russian man worked out the period of this long 586 million year cycle, and he said it's 586.2385 million years. And I thought, I wonder if you can really get it accurate. And when I follow through these ratios and come down here, the period I get for this one here, 11.86 years, and for people who know that's Jupiter's period around the Sun, and I long regarded that as a very accurate figure from which to calculate these other ones. When I do the calculation through there, it gives 11.8622, which is correct to 6-digit accuracy for Jupiter's period around the Sun. So then I said, I think he's got it right. So I used that figure for my base for calculating it all. When we get down the bottom here, 0.07 of a year is 25.8 days, and there's a whole cluster of ones related to the Sun occurring in that period. 25.8 days is the solar rotation period. As seen from Earth, it's nearer to 28 days because we're moving around as the Sun rotates, so it takes a little longer to catch up each time. So I mentioned the geological ones. There's 2 periods that there's some longer periods mentioned by the geologists. There's a guy named George Williams who lives in Australia, and there was a conference on geological cycles, and I first came across his work before I met the Russian man, and he said there's cycles of about 600 million years, 300, 150, 74 and 37. But the much more accurate figure was 586 million years for the long one. And the mass extinction events, different figures give that, but they tend to average about 26.65 million years. And what I noticed was those two, the 37 million one was 36.64 if I calculated off the Russian man's figure. And when I put those together, the red ones here are the 26.65 million year mass extinction cycle, and it forms beats with it comes into sync with 36.64 million years, everywhere there's a blue mark. So it's sort of, it's 4 or 3 of those intervals apart, it comes back into sync. And you can see here, this is from Wikipedia, the different ages that, of the geological record. And you can see that, that most of them, a lot of them are just 2 of those periods long, some are 3 long, some are only 1 long, but you can see how the geological record is showing clearly the presence of the cycle and of the beat with the other cycle, that both of them are showing up in there. It was after Dewey had done his work and after my initial work, I began to study some other solar phenomena, and I found a series of cycles. I called it a 0.4 something year cycle, which works out to 155 days about. I found it in sunspots and a couple of other solar phenomena. And then I found out that there were other people doing that as well. And there were a whole series of papers published, which I give the references to in there. 3 or 4 guys have published a lot of papers saying there are these whole bunch of cycles in the sun, and they have periods which are harmonically related. So they had observed that the solar rotation, 25.8 days, they had observed around 51, 52 days that there was a cycle, another one at a little over 100 days, another one about 155 days, another one at 464 days, another one at 77 days. So we've got ratios of 2 again and 3 this way. And if I keep multiplying this by 2, I get to 1238 days, which is 3.389 years. Now, Dewey had worked out that one of the most common cycles in the American stock market and a lot of other financial instruments, he gave a period of 40.68 months, which is 3.390. So it only disagreed by 0.001 there from the figure that I've got here. And so that actually links this whole set. It turns out that that one is a 7th of one of the other ones he had. So that shows I had the different blocks. When I showed the different blocks of these, I had it somewhere, didn't I? I must have flashed past it. This one. So this was the one that Dewey mainly did, and I've got a ratio 7 there to these other ones. And the periods come out extremely accurate, 4-digit accuracy sort of thing, when you put that ratio 7 in. And it was clear, Dewey must have noticed this because he had, in his cycles, he had 1.11, 2.22, 4.48 years. And he must have realised that fitted with 11.1, 22.2 and 44.4 years, which are all common solar phenomena, that fit in. So there had to be a ratio of 5 in there, not just 2s and 3s, but he doesn't seem to have mentioned that anywhere. I think he thought if he got too many of them, people would say, oh, you can fit everything with that, because he didn't know where to stop with his ratios of 2 and 3, so he did this funny double lambda thing. But this theory tells us where to stop. I haven't done this chart, but as you go up, like the original harmonics 1, 2, 4 are very strong. 8, 16, 32 gradually get weaker, and the series 6 comes 12, 24, 48 become very strong when you get one ratio of 3 in, and you get these little parameters coming in of how strong they are. Yeah, I'm just checking if I... how are we going to time? My second talk's long, so I can do a little bit of that now if I...
Basically over.
I'm over already?
Yeah.
I'll stop there then. That one can go for the next one.
Okay.
Are there any questions? I've done a lot very quickly.